back to part 3 of the Heathkit vacuum tube voltmeter model IM-5228. Today I thought we'd look at the schematic for a moment. This is going to be a fairly short video. If you haven't seen the part 1 or part 2, please go check those out and then come back to this one. While you're there, go ahead and subscribe and hit the notification bell to get notifications for future videos. In the next video, we'll be actually calibrating this piece of equipment. But before we get into that, I need to go through this whole circuit and make sure that the resistor values are good, the capacitor values are good, everything's connected up correctly. As you know, this was a kit and somebody put it together. I don't know that it ever worked. It may never have worked. So we're gonna have to check it out, and there may be some bad solder joints and a bunch of other things that I can find during my initial inspection, but I definitely need to go through these values and make sure they're okay. In doing that, I kind of want to show you guys how this thing kind of operates, because you're going to need this schematic in order to determine what resistors go to what terminal and all of that inside the circuit when you're testing them. Now you could, if the markings are good on the resistors itself, you can compare the readings to those, but you don't know that you're actually testing this one or this one or this one. They're all the same value. You see here, these are all this one's like 683K. I guess all these are different values here, but there are some of them in the circuit that are the same values. Like there's an 800K there and there's an 800K down here. So you know which one's which. Well, the schematic will show you that. So it's good to go with the schematic. I do not like the way Heathkit made this schematic with the actual physical representation of how the wafers are acting. These are all stacked wafer switches, rotary switches on these wafers here, and some of them are on like this one's on the front of one wafer, and this is on the back of the same wafer. So once it turns, it's doing all these different functions. What I found in tracing this out, this schematic is actually produced in a way that it is in AC reading mode, basically. I know that because the ohms scale resistors and circuit is out of the circuit at pin 2 right here. Notice it's not making any contact to any other pins. And also the probe is in the AC ohms position here. And when you look at this, you actually see that whatever signal is going to be applied here is going to be applied to this rectifier, and you don't need this rectifier in the circuit for DC. And you have two modes of DC, a negative and a positive. So I know for a fact that the way the schematic is written right now, it is for AC mode. And then you have to visualize what it would look like for the other two DC modes or the ohms mode. Now, Heathkit didn't do this for all of their kits, all of their VTVMs. In fact, here's one right here where they actually made it a little bit easier to read. It's similar to the IM-5228 here, in which the rotary switches are kind of represented by a fixed point and then contacts that this arrow kind of points to. And you can trace this out much easier. This would be for the ohms scale. This would more than likely be for the ohms range, the scaling on the ohms range, ohms function, and then this would be for the AC function, and this would be for the DC function. So, and then same thing down here. They have the different positions for the rotary switches, for the function switches. These are the range switches. These are the function switches, and that's kind of what they've done here with the AV3. So a little bit easier to read, but we're not dealing with either one of those. We're dealing with the 5228, and this is how they've got it. So if we trace this out real quick, just to kind of give you an idea of how this is operating, the power supply down here is pretty straightforward. This wafer switch right here will basically, when you turn it, it eventually get to the point where one of these contacts won't make with this contact, so you'll no longer supply power to the rest of the circuit. That'd be the off position. Right now you're supplying power to it, so this doesn't tell me what function, what position we're in. I just know it's on. But judging by this up here, I know that I'm in my AC position. So I apply an AC signal to this leaf of this phone jack here, and it goes two places. It's applied to pin 5 on this wafer, which doesn't go anywhere, and it's applied to pin 3 on this wafer. Let me make this a little bit bigger so you can see. Applied to pin 3 on this wafer. That in turn, in the position that it's in now, applies the voltage to pin 4, and pin 4 will actually supply the voltage to this wafer up here through this capacitor, and we'll basically get a voltage across here to ground. So, and based off of the position of this wafer, that's either going to be full voltage or it's going to be some voltage divider. So right now I've got 11 to 8, okay, which is going to be the full voltage, or I could have some division of that, and you can do the math here to figure out what that is going to be. It's not going to be 80% because this is not a, they're not all equal, but you can kind of think of that in your mind. So you know, it's going to be rotating over here, and it's going to hit 10 and still be on 8, or it's going to hit 9 and still be on 8. So you're going to pick up this part of the voltage divider or this part of the voltage divider. So when you're working with higher voltages, you want to be up here, you know, in one of these, because you don't want to send a very high voltage up to this. That's going to cause the meter to deflect too far. So basically right now we have full voltage. So let's say we're reading 120 volts on the 150 volt scale. That's where we'd be right here, and we're going to be sending it over here to this rectifier tube. Now if you look at this rectifier tube, at first glance you're going to think, oh wow, this is a full wave rectifier. I've got 2 diodes basically in one tube. Well, that's not quite what we have here. What we really have here is a half-wave voltage doubler. And what that would look like, basically the doubler circuit consists of these 2 diodes and the configuration they're in now. You notice that the signal is applied to the cathode, or the plate or anode on this one, and the cathode on this one. And you have a capacitor here, 0.05 microfarad, and a capacitor here, another 0.05 microfarad. So between these 2 capacitors and these 2 diodes, we're creating basically a voltage, half-wave voltage doubler circuit. In the diode world or solid state world, it would look like this, where I have my cathode tied to ground, which is what we have here, cathode tied to ground, and I have a capacitor in between the cathode and anode of one diode, and a capacitor across the cathode and anode at the other ends of the diode, which is this one right here, which you see in this circuit right here. Essentially, this capacitor is across the cathode, or the anode of this one, to ground, which is the same point with the cathode here. So essentially we get double the voltage across this capacitor. Now in this solid state circuit, ideally we would get 2 times the voltage across this capacitor, but we actually lose, you know, a voltage drop of maybe 0.7 volts, 0.6 volts, whatever it is, across this diode on the first negative, you know, on the negative iteration here where this capacitor charges up. Then on the positive iteration, we lose another, we've already lost the 0.7 or whatever across here. This one doesn't charge up quite to the full voltage, and then we lose a voltage drop across this as well. So essentially we get about 1.5 volts less than 2 VM on this capacitor, which is supplied to our load. With this being a tube, we don't have that, so we're going to get essentially pretty close to 2 times, really close to 2 times the voltage across this capacitor right here. That voltage is going to be applied to this point right here. We have a balancing circuit that goes back to the transformer down here. I don't know if I can find that. Let's see. There's the balancing point right here. That's just going to balance the AC. But eventually this voltage is going to find its way back through this network here, and depending on what position we have this range switch in, the way we have it now, it goes right, let's see, it goes out 7, 6, 5, out 6, and comes right back up to 1, 1, 9, and then applies the voltage to the grid without going through any resistors in this network. If this were rotated around, we'd start picking up these resistors right here for our scales, okay? And this is going to be the same resistors that are used for the DC circuit as well. So whether it's AC or DC at this point, it doesn't matter. Now that we've gone through this circuit right here, it's going to be DC on this line. So this is where we would be whether we were measuring AC or DC at this point. That basically is going to change the bias of this part of this triode here. Okay, think of it as a transistor or a FET or whatever. This whole section right here works on the principle of a Wheatstone Bridge, basically. If you think about a Wheatstone Bridge, you know, you got your balancing resistors, and you can tell what a unknown resistor is by, you know, matching it with a variable resistor. This is kind of the same situation. You know, put a galvanometer, you know, in your old VOM meters, your volt amp milliamp meters. That's how they work. They just basically stuck a galvanometer between a bridge, and you ran your voltage in there, and anytime it, you know, the balance wasn't right, current flew through the meter and the meter movement. You can think of this the same way. Basically, we tie our cathode in. We're in AC mode, so we're going to be going through this AC calibration pot right here, and we're going to tie it in right here. It's going to go through the meter, out of the meter, pin 5, pin 7, and we're going to tie right back to this cathode. So as long as these cathodes are at the same potential, and this one's being held at a certain bias, so there's a certain current flow through this. Once we balance that out through this zero adjust and through our you know, balancing, which we're going to do in the calibration procedures, there shouldn't be any current, or there shouldn't be any voltage potential difference between this cathode and this cathode. Therefore, there won't be any current flow through this meter. I've got a schematic right here that kind of shows this a little bit better, I think. Unless I closed it out. I may have closed it out. Okay, so I've got a schematic here that shows this a little bit better. So this is kind of convoluted here because I'm working with, you know, 3 different measurement types that I can switch in and out of this circuit here. But in reality, once one's switched in, basically it looks like this. And this is actually drawn for the DC measurement. But you can see what I was talking about. I have a balance adjust down here, which we have right here. And that's basically going to compensate for the lack of matching that these, you know, the characteristics of each one of these triodes is going to be slightly different. If they're not matched properly, I need some way of balancing that out so that I can, you know, match the current flow that's going through here and thus match the voltages. But essentially what I have here is this meter across here. Anytime this potential changes in relation to this one, there should be some current flow. And that's going to cause the coil in the meter movement to change its magnetic field and actually move the pointer on the needle pointer on the scale face. So essentially what we have here is just a bridge. So this would be the way it'd look for DC, with a DC cal here to compensate for any you know, differences in these values and how they are. And we also have a cal switch for the AC and a cal switch for the, or a cal potentiometer for the ohms adjust too. So that's going to be adjusting for, you know, the ohms adjust is going to be adjusting for the differences here. The AC cal adjust is going to be adjusting for the differences in the AC circuit. The DC cal adjust is going to be adjusting. Now, pretty much the AC circuit, once it gets to this point uses the same circuit as the DC. However, in the DC cal, you have the 1 mega ohm resistor in the probe, right? So that's going to be a change. You don't have that in the AC. So you have this 1 meg resistor right here. So this really needs to be calibrated with that probe, with the 1 meg resistor. Otherwise, you're going to be all out of calibration. So it needs to be switched in when you do that calibration. And we're going to go through that when we actually do the calibration of this meter. But that's kind of the short and skinny of this thing. I hope you guys enjoyed it. And if you did, please click like and subscribe to this channel. Go ahead and hit that bell for notifications. And we'll see you for video number 4 when we do the calibration for this thing. Thank you very much.